In this mini lecture, we're going to talk about torque. A torque can be exerted on a current carrying conductor. We take our current carrying conductor, here we have a wire in this shape, our current is running through it. We take that wire, place it into a magnetic field, and we can induce a torque, which means we can get it rotating, because a torque is a rotational force, or it's the rotational equivalent of a force. We talked about torque last semester. So we're going to consider here this rectangular loop carrying a current I in the presence of an external magnetic field. Okay, so here my magnetic field is directed in this way, and each side of my loop here will experience a magnetic force. That magnetic force has a magnitude of the current times the length of that segment of wire times B times sine theta. In my magnetic force equation, this angle theta is the angle between my current and my magnetic field. So it would be the angle between the direction of my current and my magnetic field, and in this case, that angle would be 90 degrees here. In this diagram, the forces acting on my wires on this side of my loop that has length A, the forces, the magnetic force acting on these sides of my loop is going to be 0. Okay, why? Well, because we have the direction of current is exactly along in the same direction as the direction of the magnetic field. Okay, so the angle between my magnetic field and current is 0. Sine of 0 is 0. So both of these sides of my wire are not going to experience a magnetic force on them. But these two ends of my loop here will experience a magnetic force. So the forces acting on both of these sides of my loop, we can determine the direction of those magnetic forces using the right-hand rule. Now remember, things are going to be flipped from me to you in some respects. So just consider that, okay? Maybe you want to draw this diagram on your paper and listen to the words that I'm saying, but don't necessarily follow the exact directions of my fingers in my palms, because they might be different from you because of the way that this light board swaps things. Okay, so my fingers are going to point in the direction of the magnetic field. My thumb needs to point in the direction of the moving charge. So my electron is going to be traveling opposite the direction of the conventional current. For a negative charge, it's the back side of my hand that tells me the direction of the magnetic force. The back side of my hand is pointing, from my perspective, is pointing into the loop right here, into my page. So the magnetic force on this side of my loop is going to be directed inward toward the page. Now over here, magnetic field is pointing this way. My thumb needs to point in the direction of the charge carrier, which is opposite the direction of the conventional current. The back side of my hand tells me the direction of the magnetic force acting on a negative charge, and my back side of my hand is pointing in this direction. Okay, behind me, or when I'm looking at my screen, is pointing out of the page. So on this side, we've got the magnetic force going this way, it's pushing this way, and the magnetic force on this side is pushing it back in this way. So we're going to get this thing to rotate. We're going to get this thing to spin, and that's what creates the torque. Okay, so this is the magnetic force acting on both of these sides of my wire here, my loop of wire. The magnetic force is 0 here and here. So these forces are going to create a torque, a rotational motion, a rotational force. So my equation for torque, I'll use this fancy T here, tau. Torque is equal to RF sine theta. Okay, this R, this is your distance between the rotation axis and where that force is applied. So my rotation axis, this whole thing is rotating around this center. So my loop going around is connected over here, okay? And the current's coming in on this side and is coming out on this side. So it's going to rotate around this midpoint. So this R is going to be this distance here, which is half of my length of this side of the loop. So my R is actually A over 2. Okay, that's the distance between my rotation axis and where I'm applying the forces on either side, okay? And this angle theta is different than this angle theta. So this angle theta here for the force, that's your angle between the current and the magnetic field. Now this angle theta here for my torque is the angle between my direction for the force and kind of a vector that I can draw along R, along from where my rotation axis is to where that force is being applied, okay? So this angle theta could change. But this angle theta here, sine of theta is maximum whenever this angle is 90 degrees. So you get your maximum torque when this angle theta here is 90 degrees. Okay, so actually in this image right here that I've drawn, I have maximum torque on this side of my loop and on this side of my loop because my force is either into the page or out of the page. And this vector R that I could draw would be the distance, or a straight line vector that I could draw between my rotation axis and right here where that force is being applied. And that force is directly perpendicularly in here and perpendicularly out here. And so that angle here is going to be 90 degrees when we have maximum torque, okay? The maximum torque that we can get is going to be the sum of the torque acting on this part of my loop and the torque acting on this part of my loop. So I'm calling the torque over here on this side the right side, and I'm calling the torque over here the left side. So I sum up those torques, and that will give me my maximum torque if these torques are occurring when this angle here is 90 degrees, such that sine of theta is equal to 1. That's our maximum. That's the condition for our maximum torque. Okay, so at maximum torque for both of these parts of my loop, we have sine of 90 degrees, which is 1. So then for maximum torque on the right side here, we're going to have our distance R times the force, the magnetic force that's being applied on the right side, plus my distance R times the magnetic force that's being applied on the left side, okay? So we said how this distance R, that's the distance between my rotation axis and where that force is applied. So in this case, that's A over 2. Then we multiply it by the magnetic force here acting on this wire. Our magnetic force is the current times the length. So the length of this wire, we're calling that B, times the magnetic field, okay? And also, this magnetic force is maximum when I and B are perpendicular, when this is 90 degrees. And that is the case here for this particular snapshot in time that I'm showing you for this loop here, this special case, okay? And then, so that's for this side. And then for the other side, we have our distance R, which is half this distance A. So R was A over 2 times I times the length of that side times B. Well, then we have, both of these terms are the same. So we have 2A over 2 times I little b big B. Okay, so those 2's cancel. So the maximum torque that I can get on my loop then is going to be the current times the magnetic field times the length A of my loop here times the length B of my loop here. And this quantity, A times B, we've got this side A and we're multiplying it by this side B. That's an area. That's a length times a width. So this is giving me the area of my loop here, okay? So the maximum torque I can achieve is going to be the current times the magnetic field times the area of this loop right here. Okay, so that is my maximum torque that I could achieve in this particular setup, which happens at this instant of time right here that I have depicted on the whiteboard. Now we can generalize this equation and say that the torque on my loop for any circumstance is going to equal N, which is the number of turns of this coil. I could take this coil and wrap it around itself a bunch of times. We've only done it once here for this particular problem. So the torque will be N times I B, the current times the magnetic field strength, times the area of your loop, times sine theta. Okay, and this angle theta is the angle between the perpendicular to the loop and the magnetic field. Okay, and so this is a more general description of how we can find the torque. We're going to calculate the torque on a circular loop in a magnetic field. Here I have my circular loop of wire, and I've oriented it inside my XYZ coordinate system. Here's the X hat direction, the Y hat direction, and then the Z hat direction is vertically upward. The radius of my loop, this is my radius, the radius of my loop is 1 meter, okay? And it is placed in a magnetic field of magnitude 0.5 Tesla. The normal to the plane of the loop right along the z-axis would be the normal, the perpendicular to the plane of the loop. So the normal to the plane of a loop makes an angle of 30 degrees with respect to the magnetic field. That means that this angle right here, theta, is 30 degrees. The current in the loop is 2 amperes. Find the magnitude of the torque at this instant. So here's my wire, and I'm just going to say that the current is running around in this direction here. We need to find the torque of this loop of wire. Our equation for the torque is just equal to the number of coils in my loop here times the current through the loop times its area times the magnetic field times sine theta. In our torque equation, this angle theta here, that's the angle between our magnetic field and the perpendicular to the loop. So here's my loop, perpendicular straight up along the z-axis. So this angle theta here is still this 30 degrees. Okay. Now we only have one turn of this loop. It's only wrapped around once. Okay. So N in this problem is just 1. And so since this angle here, oh, that's 30 degrees, right? So this is going to equal the current times the area of our loop. We have a circle, so the area of our loop is going to be pi times the radius squared times the magnetic field times sine of our angle 30 degrees. Okay, so our torque is going to be 2 amperes times pi times r squared. So we're going to have 1 meter squared, and then we're going to multiply it by the magnitude of our magnetic field, 0.5 Tesla, and then times sine of 30 degrees, okay? Now, anytime we're using an angle in degrees, angle in degrees, angle in degrees, you use your calculator in degree mode, okay? So now we got to multiply all of this stuff out, and we find that our torque of this loop, it's got a current running through it, is subject to a magnetic field, so it's going to experience a torque. That torque is 1.57 Newton meter. So if you remember from last semester, the unit on torque is Newton meter. Now, how did we get Newton meter from all of these units here? Well, let's think about this line here. So I've got the current, which has units of amperes, okay? And I'm multiplying it by my area, which has units of meters squared. And then I'm multiplying it by my magnetic field, which Tesla can also be written as kilogram over ampere seconds squared. Okay, so I see that my ampere cancels with my ampere, and this leaves me with the units of meters squared times kilogram all over seconds squared. Now, if I write it, let's write it like this. We've got kilogram times a meter over a second squared times another meter. And that gives me got to have my meter times meter. This quantity right here, kilogram meter over second squared, is a Newton. So that's how we get, from all of these units, this is how we get a unit for torque of Newton times meter. Okay, so if you're ever curious how do those units come about, you can always perform the unit analysis like this. And I don't always remember, some of these equivalencies for the units. I had to look up that a Tesla can also be equal to a kilogram ampere over seconds squared. I had to look that up on Wikipedia. But I got that there, and then I can show that these units do in fact give me the units of Newton times meter for the torque.